Section 2.7, Modeling with First-Order Linear Ordinary Differential Equations. The notes in this section are pretty detailed. Instead of trying to crank through a bunch of word problems without really understanding what's going on, I wanted the notes for this section to focus on the process of creating and interpreting a differential equation model. So I have typed a lot of detailed explanation in these notes, much of which I won't be directly explaining in this video. So I definitely encourage you to download the notes and work through them in a careful way at your own pace in addition to watching this video. So as I explained in the opening paragraph, the term modeling in a math class generally means we've tried to create a mathematical equation or set of equations that captures the important properties of a relationship between at least two quantities. Sometimes I'll describe this as mathifying the relationship. It's often true that we not only want to model the values of the quantities under consideration, but we also want to model the rate at which the quantities are changing. This will lead our mathematical model to take on the structure of a differential equation. This is, of course, why we're studying this topic in this class. My claim in this fourth paragraph is a little exaggerated, but it's only a little exaggerated. Pretty much every formula you have encountered in a science class, think of the laws of motion in physics or equations governing circuits in an electrical engineering class or fluid flow, all of those formulas are either themselves differential equation models or they come from differential equation models, usually as like a special case of a more general differential equation model. So the process that we're demonstrating in this section translates to pretty much every other science or engineering course you'll take. So my goal for this section, as I've stated here, is we want to develop one or two models ourselves. We also want to analyze a couple of established models that will be presented in their completed form. And then in conclusion, at the end of the section, I'm going to present some general principles that give helpful strategies in contexts in which we need to build a differential equation model ourselves. So let's give it a shot. The first context I want to look at is a mass on a spring. I want to start from the most basic ideas or principles and build up to a robust mathematical formulation of what's going on in this context. As I've noted here, in this for example, we want to demonstrate the process of constructing a mathematical model. We don't want to focus necessarily on actually solving the resulting differential equation. So in this situation, we want to model the motion, or to be more precise, the position of a quote-unquote mass. This mass could be lots of things. I usually just draw it as a box. The mass is connected to a spring, which in turn is connected to some kind of support. We generally think of this support as fixed and motionless unless otherwise noted. I've got a picture here which shows an example of this setup. So in the picture, I've got a spring. On one end of the spring, it is attached to a fixed support. On the other end of the spring, we have our mass, which in this case is just some weight. In this particular picture, they've got a second spring for reference. This is what this spring would look like if there was no mass hanging from it. And then they have arranged it so that the mass hangs next to a meter stick so that they can take measurements. So this is kind of one example of the situation that we're trying to model. Here's another picture that this time the mass is resting on a flat surface. In this formulation, or from this perspective, I think of this solid support as being a wall or some fixed structure. And then the mass glides along the surface, oscillating back and forth as influenced by the force of the spring and some other properties that we'll try to model here. So how do we build a mathematicalization of the motion of this mass? Our starting point is going to be pretty preliminary. We want to start by identifying independent and dependent variables. We believe the position of the mass, more precisely the position of the mass with respect to like an equilibrium or rest position, we believe that that position changes over time. So our dependent variable is position. Sometimes we'll call this distance or displacement. And as indicated in this second picture here, I'm accustomed to representing that variable as x. And then our independent variable is going to be time. Note that we have to make a choice about what we consider to be positive x values versus negative x values. As I explained here, it's common to think of stretching the spring as yielding positive x values. That's indicated in this picture. Our equilibrium or rest position, if I just let the mass sit on its own, it would be here at what's labeled x equals 0. I have stretched the mass past that equilibrium position, and so I would consider that x value or that displacement to be positive. The opposite is true as well. If I compress so that the mass is to the left in this representation of that equilibrium position, then I would consider that displacement to be a negative x value. So how do we mathify the relationship between position and time? The key to capturing the structure in this example is to analyze the forces that are acting on our mass. In particular, there's 3 forces that we want to focus on. I've labeled them here. First, we want to think about the force due to the spring itself. We're going to call that force F sub S. Next, we want to think about the force due to friction. And here I'm thinking of friction pretty generally. This could be air resistance, or this could be the actual friction between the mass and the surface that it rests on. Either way, we're going to denote the force due to friction as capital F sub little f. And then we also want to account for any external force that could be acting on our system somehow. We'll label that as capital F sub E. In any model, we have to limit our focus to a few specific quantities or features of the model. In this case, these three forces that are acting on our mass are going to be the 3 primary components that work to build our model. Take a second to read my little note here about gravity. The punchline is that we're not going to include the force due to gravity. I try to explain it there. So this is a little strange because our focus has temporarily shifted from position over to forces. So how do I transition back? This is the key step here, is that we need to utilize established physical laws. This is a pretty common trick when building a mathematical model. And so that's what we're going to rely on here. Now, let me demonstrate what I mean. We've got these 3 forces. So what laws govern the forces, the quantities that we're interested in? As you may know, Hooke's law relates to the force exerted by the spring. Hooke's law states that the force exerted by the spring is going to be proportional to the displacement of the mass. So let's think about our previous choice of what's considered positive and negative when dealing with our x values. Specifically, if I imagine stretching the mass out past its equilibrium, I intuitively conclude that the spring will be pulling the mass back toward the equilibrium. So the important takeaway here is that the spring's force would act in the opposite direction of the displacement. This allows us to write our force due to the spring as negative k times x, where k is some positive spring constant that measures the strength of the spring. X is the displacement of the mass, and the product of those will give us the force that is being exerted by the spring. Next up, the force due to friction. Now, friction can be complicated. There are many different types of friction. There's air resistance, there's friction between 2 surfaces, static friction, etc. For our purposes, we're going to use the assumption that the force due to friction is proportional to velocity. And then again, it makes sense that this force is acting in the opposite direction from the velocity. So if I have a positive velocity, my mass is moving positively away from the equilibrium, friction is going to act in the opposite direction to slow down that motion. So we can write that the force due to friction will be some proportionality constant, here I've labeled as gamma, times the velocity. And again, that's negative. But you remember from calculus that the velocity of an object is simply the derivative of the position function for that object. So instead of writing this force due to friction in terms of velocity, I can actually write it in terms of position. Well, not position directly, but the first derivative of position. Lastly, we have the external force. This is meant to be completely general. Any external influence on our system. Maybe a piston is attached to our mass that forces it to oscillate along with or in competition with the spring. Maybe the mass experiences a sudden jolt like your car's shocks would experience when you hit a hole in the road while you're driving. So there isn't any restriction on this external force. So we're just going to represent it as a generic function of time. And I'm just going to say that the external force is some function g of t. So we have three separate forces acting on our mass. How do we bring them together into a single model? The unifying factor here is Newton's second law. So Newton's second law states that the sum of all forces acting on our mass should equal the value of the mass multiplied by the acceleration of the mass. So let me do that. Let me take the three forces that we've identified. Here I've listed them in this equation form. The force due to the spring, the force due to friction, the external force. I'm going to sum those up, and Newton's second law says that those have to equal mass times acceleration. I have other expressions for these three forces, at least these two on the left. So I can drop those substitutions in, and that turns my equation into this here. And then you also remember from calculus that the acceleration of an object is given as the second derivative of the position function. So in this equation, instead of this a on the right-hand side, I can make the substitution that a is equal to x double prime. If I rearrange things a little bit, I end up with this equation here. And this equation here, as simple as it seems, tells us pretty much everything we need to know about the position of this mass on a spring. We will investigate this equation in lots and lots of detail in the next chapter. For now, the purpose of this example was just to demonstrate the procedure that would lead us to a differential equation model like I have in this box here. So for the purposes of this example, we're not going to try to push forward and solve this differential equation, but we will spend lots of time working with this differential equation in chapter 3. All right, let's take a look at another example. This time we'll not only set up the differential equation model, but we'll also solve the resulting differential equation. The context for example 1 is the mixing of liquid solutions. We're told that a tank initially contains 600 liters of water with a sucrose concentration of 0.2 kilograms per liter. Let's just stop there for a sec to make sure we understand even this first sentence. We've got 600 liters of liquid in a tank to start. That liquid is primarily water, but that liquid has some sucrose mixed in with it, dissolved into the water. So there's 600 liters of solution in the tank. Most of it's water, but there is some sucrose. How much sucrose is in the tank? Well, initially the concentration is 0.2 kilograms per liter. All of these numerical quantities are going to play into the setup of my differential equation model in some way, so I'm going to highlight these numerical quantities. So that first sentence tells us what's happening at the beginning, what the properties of the liquid in the tank are initially. The second sentence indicates that we start to add a solution. This solution is also comprised of sucrose and water. This solution that we're adding has a lower sucrose concentration. There's only 0.1 kilograms per liter, and we're adding that solution into the tank. How fast do we add that solution? We're going to add 40 liters every minute. The next sentence is a little unrealistic, but we're going to assume that as soon as that solution enters the tank, it immediately becomes dissolved with the solution that's already in the tank. And then we're told that the resulting solution leaves through a spout in the bottom at 20 liters per minute. So if we just compare that, we could tell that the amount of liquid in the tank must be increasing because we're adding liquid at a rate of 40 liters per minute, and liquid is leaving at a rate of only 20 liters per minute. So the amount of liquid in the tank is increasing. Hopefully it doesn't overflow. But what we want to focus on is the amount of sucrose in the tank at any given time. And it might be helpful to pause and try to identify what the units on this dependent variable would be. Notice that in the problem, when we talk about sucrose, we talk about how much is concentrated in the solution, but our dependent variable should be the actual amount. So this is mass, so this is actually in kilograms. So one of our tasks will be to understand how we can convert these concentration values into direct amount values. So as I said, our goal will be to set up a differential equation which captures all of these properties and then actually solve the resulting differential equation. I'll start by drawing a picture just to clarify exactly what's going on in this particular situation. This is a pretty crude drawing, but you get the sense. We've got some tank and we've got liquid flowing into the tank at a certain rate that mixes with the liquid that's already in the tank, and then liquid flows out of the tank at a certain rate. I can label the rates at which the liquid are entering and exiting the tank, and now I can start to set up my differential equation. First, I want to note a fundamental detail about the structure of my model, namely that the rate of change I'm trying to describe, the rate of change of the amount of sucrose in the tank with respect to time, is the difference between the rate at which sucrose enters the tank and the rate at which sucrose leaves the tank. This quantity on the left is exactly dy dt, and the quantity on the right, for now, I'll just label these rates R sub in and R sub out. Now let's look at those two rates individually. We know the amount of liquid entering the tank has a rate of 40 liters per minute. We additionally know that this liquid has a specified concentration of sucrose, namely 0.1 kilograms per liter. So simply multiplying those two quantities yields the rate at which sucrose is entering the tank. So this product is our R sub in. It's helpful to verify by looking at the units in this product. Here I have liters per minute multiplied by kilograms per liter. When I multiply those, the liters cancel, and so I'll be left with 4 kilograms per minute. R sub out is not quite as simple. First, over here in the margin, I note that the concentration of sucrose in the tank at any given time is a fraction. The amount of sucrose in the tank divided by the amount of water in the tank. This numerator is exactly the quantity we're trying to model. We can label that y or y of t. I've written the denominator as 600 plus 20t. Remember that the tank started with 600 liters of water, and we've already noted that if 40 liters of water are entering every minute and only 20 liters of water are leaving, then overall the amount of water is increasing by 20 liters per minute. So I had an initial amount of 600 plus an additional 20 liters every minute. The structure of our R sub out calculation will now be the same as the structure of our R sub in calculation. I'll take the rate at which liquid is exiting the tank or leaving the tank, and I'll multiply that by the concentration of sucrose in the liquid leaving the tank. This second quantity, the concentration, is exactly the quantity that I just calculated over here in the margin in green. Multiplying through, I have an expression for R sub out. And putting all these ingredients together, I now have built my differential equation model. Note that this differential equation is first order, and after some simplification, I can see that it is linear. We've had lots of practice solving first-order linear ODEs recently, so I'll work through the details of solving this differential equation pretty quickly. So here's my general solution. As always, my work got a little cramped here. Over here in orange, I calculated the necessary mu of t. I multiplied through by that mu, And then I skipped a couple steps to get to my general solutions here. It's worth pointing out what we've accomplished with this general solution. Our initial model captured the essential properties of this situation, but it did so in terms of a differential equation. We could not directly deduce or predict values of y straight from the differential equation. That's not because our differential equation was wrong in any sense. That's just the nature of a differential equation. By solving the differential equation, we get a function which does directly model our quantity of interest in terms of the independent variable. So now I can directly calculate sucrose amounts in the tank at a specified time. Both our original differential equation model and our general solutions here are correct models. They just have different natures. To distinguish between these types of models, I'll sometimes refer to a general solution like this as a function model. Do we have any initial conditions? Well, we've already stated that the initial amount of liquid and the concentration of sucrose in the tank, so these can be used to define an appropriate initial condition. Over here on the left, I've tried to squeeze in that initial condition calculation. We know there are 600 liters of liquid in the tank initially, and we're told that the initial concentration is 0.2 kilograms per liter. So multiplying those indicates that there are initially 120, the units would be kilograms, 120 kilograms of sucrose. I can plug that in, incorporate that initial condition in the usual way. Let me just go ahead and write out my final solution. Again, I've tried to squeeze in that solution here. You'll notice that incorporating this initial condition indicates that C should be 1800. So my final actual solution is here, y equals 2t plus 60 plus 1800 over t plus 3. So again, this can be used to predict or calculate specific sucrose amounts within the tank at any time t. So in this example, we not only took the verbal description of the scenario and translated that into a differential equation model, but we also used the appropriate solution technique to solve that differential equation. This resulted in what I called a function model, which has the benefit of allowing us to directly calculate values of our desired quantity by plugging in values of the independent variable if we want. In the notes, I've provided a few more examples of this nature. Some physical situation is described with the intention that we translate that description into a differential equation model. For the sake of time, I won't work through the details of constructing these models, but I have stated the differential equation model for each example. When you have an extra minute, take the time to see if you can translate the written description that's provided and see if you end up with the same differential equation model that I have listed here. As I said, I've provided 4 examples, for example, 2, 3, 4, and 5. I've pointed out here in the notes that the differential equations we're ending up with aren't extremely complicated. For me, the hardest part of these problems is the initial setup, taking the written description and translating that into a mathematical formulation of the situation. But once that step has been accomplished, moving forward from there to actually solve the resulting differential equation shouldn't be too challenging. The next thing I'd like to do is sort of reverse the process. Let's start by taking an established differential equation model and seeing if we can identify features or properties of the situation as being modeled. If you look all the way back to our very first set of lecture notes reviewing differentiation and integration, you'll see the following population model. At the time, I didn't identify that this is a differential equation, but now we recognize that that's exactly what it is. Suppose all we're told is that this differential equation models the growth rate of a population, dp/dt, as indicated here. What properties can we glean about the population that we're modeling? Let's look at these 2 factors one at a time. First, we've got Kp. This first factor, Kp, indicates that the growth rate is essentially proportional to the size of the actual population. So I'm imagining ignoring this second factor here, and I would simply then have a differential equation of the form dp/dt equals Kp. And that's saying that the growth rate is proportional to the population size, according to this proportionality constant K. Since we're told little k is positive, we're trying to say a couple things. First of all, that according to this factor, the growth rate would be positive. Little k is positive, p is positive. Also, as p gets larger, since little k is fixed, as p increases, dp dt would increase. This is the idea that as the population grows, it reproduces at a higher rate. So if your elk population is small, maybe they're constantly trying to survive, and so they don't have time to reproduce. As the elk population gets bigger, they have the ability to reproduce at a higher rate. Actually, this portion of the model is a simpler population model. Let me note that over here on the side. This simpler model is sometimes used as the most preliminary, the first most basic population model. And again, it just says that the growth rate is proportional to the size of the population. This is a separable differential equation. You can move the p over, solve, and then this is a solution. I've written p sub 0 to represent the initial population. I haven't worked through the steps here, but you can try that out and verify that this simple population model leads to this solution. So just to reiterate, if I just look at this first factor, it's essentially telling me that my population is growing according to exponential growth. So what does this second factor tell us? 1 minus p over k. We can deduce that k is a specific population value, and we're going to think of k as being fixed. So let's assume that to start that like the population is less than, so p is less than that fixed k value. If p is much smaller than k, then this overall fraction would be very small. And so this overall fraction for p-values that are much smaller than k is essentially negligible. So if that fraction is essentially 0, then this second factor is essentially the number 1. And so as I've noted here, if p is significantly less than k, that fraction p over k is essentially 0. And so my model reduces to this simpler model. And so the population would more or less be experiencing exponential growth. As p grows and becomes closer and closer to k, this fraction p over k is going to approach the number 1. In my differential equation, as this fraction approaches 1, this overall second factor approaches 0. So then if I multiply kp times 0, more or less this right-hand side is essentially going to 0. So as p approaches k, the growth rate of the population approaches 0. The population is flattening out. The last case to consider then in terms of this second factor is the case where p is greater than k. If p is greater than k, then this fraction is greater than 1, and so this overall factor would be negative. That would lead the derivative on the right-hand side to have a negative value. So these types of properties might be the types of properties that would be given in a verbal description of this situation, and then our goal would be to translate those into a differential equation. Here we flipped the process. We started with the differential equation and we tried to glean those properties based on interpreting that differential equation. In the notes for that first lecture, I actually created a visual representation of possible solutions of this differential equation model. It was basically a visualization of the properties I just stated. Let me go ahead and reproduce it here. Here we have the p of t axis on the vertical axis. We have time on the horizontal axis. And then I've sketched a few possible solutions of this differential equation model based on the properties that we just identified. We know that if p equals exactly k, then the derivative is exactly 0. And so I've drawn a perfectly flat line representing a population that has a 0 derivative. It doesn't grow, it doesn't shrink. As we just stated, if the population is less than this threshold value, I expect the growth rate to be positive. And as the population approaches this threshold value, the growth rate levels out. And so the growth rate dp dt approaches 0. On the other side of the threshold, if the population is greater than this threshold k, then my population will be decreasing and it'll have a negative slope. As I mentioned in the previous lecture, this model is called the logistic growth model. This k value is what's referred to as a carrying capacity. And so this is just trying to capture the phenomena that the population will grow exponentially, but then as it reaches some threshold, some sort of maximum viable population, the population growth rate will level out. So this is the point at which resources start to become scarce, and so the population can't grow beyond that carrying capacity k. I haven't done it here, but maybe you can go back up to the population model and actually solve that differential equation. It's first order. It is separable, but it's a little tricky because you have to use partial fraction decomposition to do the integral. But maybe that's an extra challenge if you want to go back and actually try to find the general solution of this differential equation model. This picture here should feel sort of familiar. This maybe feels similar to what we call direction fields or slope fields back in section 1.2. Those were a tool that we used to derive properties from a differential equation without solving the differential equation. So if you don't remember those, go ahead and take a look back at section 1.2 as a quick reminder. The tool of a direction field is particularly effective, as I've stated here, when our differential equation has a specific property. The property is that the independent variable is absent from our differential equation. To put that more formally, our differential equation has the form dy dt equals f of y. F of y is just an expression which only contains y's, no t's, no independent variables. This type of differential equation is called an autonomous equation. If you look back over the last several examples, EG2 through EG5, as well as the population model that we just analyzed, all of those are autonomous. Our author has a section in which he specifically looks at details of autonomous equations and properties of their direction fields. This is section 2.8. It's titled Equilibrium Solutions. It's a pretty fun section and it's not very challenging, so I would encourage you to take a look at it. But for the sake of time, I'm not going to discuss it here, and I don't have a separate lecture on that. That essentially concludes what I want to say from this section. There is one last page of notes on the very last page. I've included a list from another differential equation text. This text is by Boyce and DePrima, and this is a list that they provide as a summary of steps or strategies for trying to build mathematical models. We have demonstrated the process a few times in these notes, but I just wanted to leave you with this list as an extra resource if you do find yourself trying to build a differential equation model on your own in the future.